given to us by Piero Armenante. So Piero is professor of chemical engineering and the director of the pharmaceutical engineering program at the New Jersey Institute of Technology. And he's going to talk to us about mixing in the pharmaceutical industry. Thank you very much, Piero.
Thanks, Joelle, for the kind introduction, and thanks to the organizer for inviting me. So I'm very happy to join this distinguished panel and group of people that I cannot see, but I'm sure joining from all over the world to discuss mixing once again. So at this point, I'd like to start sharing, if I can, my presentation. Can I do it myself, or do I need to have some permission from you, Joelle?
You should be able to do it yourself with it, no problem now.
Okay, let me see.
Click on the green button.
Yes.
Yep.
Got it.
Good.
Okay, I assume that you can see this now, right? So I want to discuss with you some issues that we have been working on regarding the pharmaceutical industry. So this is a pretty ambitious title because in principle covers quite a lot of potential issues in the pharma industry. Now, mixing in the pharma industry is mixing of single and multi-phase systems is an extremely common operation, which is encountered in a countless number of processes in the industry. And here just a kind of a short list of what you can find, which is pretty much what you find in many other areas in which we deal with in mixing. So I will not spend any time here. And what I like, however, to stress is the fact that, as you can see from this slide, there's a wide variety of scales at which mixing is important throughout the industry, from the small scale, the lab scale, to large fermenters and reactors and tanks that are used for production purposes. So back in 2018, we had a North American Mixing Forum conference, the 26th version of that, organized by Luis, Clara, and me in Puerto Rico. It was a quite successful conference, in my opinion. And there was a panel discussion dedicated to mixing issues and challenges in the pharma industry. So I still have the slides that the speakers that contributed to that discussion, that panel. And I just summarize a few of those slides here. So here are some excerpts for the discussion that follow. And one of the key important factors that people point out was the fact that in many cases, the industry uses equipment that's been sitting there and operating there for that matter, for decades. So there's the issue of systems that have been on operation and for quite a while, but have been designed for a number of years, and for which there's very little that you can do in terms of upgrading. So these legacy designs are still there, still be actively used, and in many cases, it's convenient to start characterizing them because in many cases, people have not done so. In addition, there's a perennial problem of regulatory aspects that restricts the ability to change process once it is created, and therefore, if a process had been started in a certain setup, it would be very difficult to change it. So other issues that, again, came up during that discussion were crystallization, which is an important topic in the pharma industry that's now received significant attention, in my opinion. Biologics, and especially the use of systems of this disposable system that at the beginning were working appropriately given the crudeness of the approaches, but now require more sophistication also from a mixing perspective. And finally, I selected this issue of validation because the pharma industry is a heavily regulated industry, and the Food and Drug Administration in the US, the EMA in Europe, and the Japanese regulatory agency all have to validate the process, have to, the manufacturers to show that they are always in control of the process. And so who makes the decision of what it is valid? So the industry always, the company in this case, comes up with the design, goes through to validation tests, but then eventually they have to prove this to the FDA. And the FDA regulators typically, as you can see here, is they're not engineers usually. So you have to convince them, and they're more easily convinced by experiments than by modeling. So there's still a gap between experiments and simulation. But as we get better and better with simulation, some of these issues may trickle down also to the regulators, who may start accepting some of these approaches that are more based on computation and not also only on experiments. So I've been interacting with industry in a variety of ways for many, many years. So both as project sponsored by them, I work at one point in time even in the pharma industry or as a consultant. So here are some of the current projects that I've carried out in recent years in my lab with my students that deal with some issues dealing with some of the validation aspects and the regulatory aspects when it comes to determine the actual process that occurs to validate some of this the dissolution processes that simulate what happens in the human body. So I will elaborate this in a moment. We also look at large-scale systems. In fact, this was actually something that came from industry directly, and in which they don't use baffles, they use angle-mounted systems, angle-mounted impellers, and velocity computation and power dissipation, stir tanks, and a variety of legacy kind of reactors and systems. So suspension, achievement of liquid level, a complete dispersion under different liquid levels, and so on. So I will not be able to talk about all of them here. So I will primarily focus on one project, which is the one you see highlighted in red at the top. And perhaps if I have time, which I'm not sure I will probably mention at least a couple of slides for the other two projects. One dealing with determination of power in stir tanks equipped with retreat blade impellers, and the other one with the suspension or the ability to detect suspension, which means NJS, in industrial tanks where you cannot see through. So let me now jump to another presentation, which is this one, that deals with the study, the hydrodynamic characteristics of a particular type of system that is commonly used in the industry, that is used to determine the rate of dissolution of tablets. So it's a test that every single company must do prior to filing for a new drug application, but also as they go into production, because they have to test every single lot using this kind of technique. So I need to give a little bit of an introduction, because I guess most people will not be familiar with this kind of processes. I should also mention that Chalakar, the student who actually worked on this project in very intensely and high quality, is also the winner of the North American Mixing Forest Student Competition. In fact, this is actually a significant chunk of this is her presentation when she gave it to the ICG meeting, although she should have gone to Niagara Falls, but meeting, as you know, was canceled and postponed. So unfortunately, she couldn't go there. Anyway, so the idea here is the following: that the FDA, the Food and Drug Administration, let me see if I can reduce this. Okay, the Food and Drug Administration requires that companies utilize standards tests to prove that their manufactured goods comply with the quality of the product that they expect. So it is actually a three-part game here. You have the pharmaceutical company that needs to prove to the FDA that their drug can be released for the public. But to do so, they need to use a variety of tools that are based primarily on the standards that are developed by the pharmacopoeia. So in the US would be the US pharmacopoeia, which is pretty much the one accepted throughout the world with slight modifications. So the USP develops this standards, and typically pharmaceutical companies use them to show to the FDA that they are in compliance when they do certain type of tests. So in fact, the project I'm discussing now is actually sponsored by the USP because they also realized there was a need to understand better the hydrodynamics. And it's also sponsored by Merck, who have also great interest in this kind of situations. So this test, the solution testing, on the one hand, try to mimic what happens in vivo in the human body by in vitro testing, but also are required to release products on a daily basis. Okay. So there are a number of dissolution tests that the USP has approved, and these 7, the most common are those 2, apparatus 1 and apparatus 2. So apparatus 1 and 2 rely on placing a tablet, in this case if it is a basket, which is apparatus 1, inside a basket, and then determine the concentration evolution over time as the drug is released into the solution as the basket is rotated. And in order for a company to be able to release the product, they need to produce curves during their experiments that are statistically similar to the curve that they file with to begin with the FDA. And if that's the case, the entire lot is discarded. So of course you can imagine that even a system as small as that, the hydrodynamics plays a key role, and I'll show you that in a moment. However, the result of a number of these tests fail, and therefore this is typically extremely costly, produces recalls, cost investigation, and products delay. So that industry tries to avoid that as much as possible. So we have shown, at least for USP2, the other type of apparatus, that some of this poor reproducibility can be caused by the hydrodynamics of the system. So we have done quite a bit of work with USP2, and we published over the years a number of, as I said, a number of papers. But now we look at USP1 because so far been very limited information in the literature on this. So this is how these things look like. There's typically a number of similar systems, so you can test a number of tablets at the same time. Each one contains, is made of this vessel, which is unbaffled, in which you rotate this basket that contains the tablet typically. So there's a need to understand how this process works. And of course, the hydrodynamic plays a critical role in a variety of these sub-processes that happens during the deletion process. And we examine, and I would say all of them, or almost all of them, but now in this presentation, I'll focus only on a few of them. And specifically, we look at apparatuses in which, again, just look back for a moment. We look at a basket dissolution testing apparatus in which we change the fill volume, we change the different types of basket people can use, and we change the rotation speed, which is, again, very typical in the industry. So here's what we did. We change agitation speed, liquid fill volume, basket mass size. And to do so, we utilize both a computational approach, but especially an experimental approach using PIV. So here is a schematic of the standard PIV system we used. But since in this case, the USP wanted to have a complete mapping of the process of the flow field, they also require us to test and to monitor the velocity, not just on the vertical plane, but also a number of horizontal planes that you can see depicted here. So we examine the velocities everywhere along this, what we call isosurfaces of these planes. And when we look at the 900 milliliter case, because typically these are the two that people use, we also have to explore more such isosurfaces. Also, we looked at a variety. I mean, the typical cases would be 40 mesh, which is the most common, and as you can see, it's a very fine mesh, to larger mesh, because as you may know, the larger the mesh size, the smaller the opening. So 10 and 20 mesh have larger openings than the 40 mesh. In addition, we use CFD to model the system, and I will skip some of the details. I will just point out, because it will become important later, that there's a clip that keeps the basket in place. And this seems like a minor issue, but actually we found out that these clips play a significant role, and they are now in the USP. In other words, they are codified, so to speak, and therefore users have to have these clips, whether they like it or not. In fact, some manufacturers of these pieces of equipment have what I call ornamental clips that people can put, although the basket is secured to the shaft in a different way than through the clips. So let me start discussing a little bit of the results here. So as you may imagine, this is an unbaffled vessel in which there's an impeller, if you want to call this the basket an impeller, that spins around. And as you move up in the vessel, you get, of course, larger and larger cross sections, some of which we could see if we're below the basket itself, otherwise some portion would be obscure. But you can imagine that this would be essentially a flow that spins around, right? And it rotates with the basket. As we increase the size of the mesh, or excuse me, the size of the mesh, which means the opening, then we'll start seeing that the intensity of the flow increases, which you can also imagine. And if you go to a larger size of opening, so 10 mesh, which is, again, the large opening in the mesh itself, you can see that now the velocity increases significantly. So we proved this time, through this kind of work that, yes, basket of different mesh size create a different flow field that may affect significantly all the results that people get. Some of these concepts were already intuitively understood by the people who work in this field. In fact, investigators at Merck told us that there was something funny happening when they changed the basket size, and now, of course, we were able to confirm it. So in summary, as far as this part is concerned, you can see that as you go from 40 mesh to 20 mesh to 10 mesh, you see a different evolution of the process in terms of the velocity. But even more dramatically, by the way, let me just show you this now since I have it. This actually is the results of the PIV measurements over time. As you can see, it is a very dynamic flow. And this is not, again, it's not CFD, this is PIV. When we change to 500 milliliters, some of the same phenomena occur, but you will see in a moment that this jet that emanates on the side becomes quite important. So in fact, let's go back for a moment to the 900 milliliters filled vessel. What we notice is that when we change the basket mesh size, a number of phenomena occurs. Overall, the flow intensity increased, but also the angle emanating, the jet emanating from the side of the basket increased in angle and in intensity. So clearly you can see here this type of recirculation pattern, which is extremely important because as the tablet disintegrates, some of this material may actually fall in granules to the bottom. And therefore, if this material is not suspended, it forms a cone. So clearly changing the mesh size of the basket has a significant impact on the flow itself, the macro flow, if you like, but also on the ability of forming cones, and as I will show in a moment into a video. So the angle, as I said, is significant and changes. And as a result, also the cross-section swept by higher velocity vectors increases as well. So here is a quantification of that angle. And as you can see, there's significant change in the angle itself, which changes, of course, the nature of the flow, especially at the bottom of the vessel. And here's a cross-section, is a measurement of a vertical cross-section that we utilize not just to look at the velocity flow field, but we also utilize to look at the actual flow that goes through the basket, which of course is extremely important because the higher the flow through the bottom of the vessel, which is also meshed, generates a higher or lower rate of dissolution. So just to see this better in a way, some of these velocity vectors we obtain experimentally are now superimposed on an image of the actual glass tank. And you can see here that now these vectors enter the bottom of the vessel, the bottom of the basket, sorry, and impact the top. And as a result of the impact in the solid top of the basket, then produce this jet, this recirculation pattern, which is also affected most likely by the small clips that are there to, in principle, retain the basket. What was important for us to see was the fact that we were able to close the mass balance. So what we did is we calculated the flow in the through the basket. And of course, we had to do this to an approximation, or this is a summation as opposed to an integral. And we did this also for the flow in, as I said, typically from the lower portion of the basket, but also we measure the flow out. And of course, what goes in must go out. And we're able to close actually the mass balance pretty satisfactorily to about 5%, 6%. Again, this is all experimental work. What is important, especially for the operator of this kind of systems, is that, as you can see here from this graph, the flow rate going through the basket and therefore affecting the dissolution rate of the tablets that sits in the basket changes, I would say, dramatically from about 4 milliliters per second if you have the 40 mesh basket to about 7 if you go with a larger size. So of course, there's a significant difference in the rate of dissolution that people expect. So this basket is obviously not interchangeable. This is, again, something that anecdotally the investigators that work with this system kind of figured out on their own. In addition, the fill volume has a significant impact on the type of flow which is established in the system, because it determines also the angle of the jet emanating from the side of the basket itself. So in one case, you can see that this 900 milliliter, with everything else being the same, produces a jet which is much stronger, therefore a stronger recirculation pattern, especially at the bottom, as opposed to a 500 milliliter jet, which, because of the proximity of the free surface to the origin of the jet, forces the jet to be much more horizontal, which is something we observe in completely different systems, essentially in stir tanks, under the circumstances in which we lower the liquid level. So here it is. So here is, again, an image, actually video, of 3 different situations, which you can see now the granules being sitting at the bottom of the vessel. And this is when we operate things at 40 mesh as opposed to 20 mesh, 10 mesh. And you can clearly see that in the 40 mesh case, a significant accumulation of this material. In fact, I can animate this. You can see this material sits at the bottom. Here you have better suspension of the particles at the very bottom. And here is even more so. So clearly it makes a big difference to use different baskets. Not just because of the fact that as a result of the higher flow through the basket, the tablet may dissolve faster, but also because of the suspension ability or lack thereof of the particles that come from the tablet and now are sitting now at the bottom of the system. All right. So we also carried out a simulation. I will not spend too much time on this. And there's significant agreement, I would say, but details are important. So here we go. In some type of simulation, we did not include the clips, thinking that at the beginning, at least, there was a simpler system to look at. But then were forced to include the clips, and the result was, as you can see now, the formation of a jet, not this jet, which may not necessarily have the perfect angle, at least for the 500 milliliter case, because it was more horizontal, but at least starts capturing some of the essence of the flow that we observe experimentally. So in conclusion, something actually I should have mentioned before, but I did not. We were forced to use extreme calibration approaches to make sure that every system was as centered as possible. This is an unbaffled system with a small device that rotates inside it, and therefore symmetry becomes key. And we were really forced to go to to significant degree of alignment of all the components. We went crazy with that, quite frankly. But once we got there with kind of reproducible results, although as you may have seen before, nothing is perfectly symmetrical in the actual experiment as opposed to the simulation. So the flow is typically somewhat nearly symmetrical. There's a poor stir region, no matter what, at the bottom of the tank that may become less so if we use mesh that had larger openings. The velocity distribution very significant with mesh size and, of course, increasing with agitation speed. But the liquid jet seems to be a critical feature that this contributes not just to the aerodynamics of the system, but also to the dissolution process that occur in this kind of dissolution tested system. So that was a decent agreement between the CFD and the PIV, but this is again something that we're conducting at this point in time, and you'll learn more about this. We have already published a paper. Another one is almost published because we just got reviews and they're very favorable. Let me know if you need any copies of this. And I'd like to acknowledge the support of 2 grants, one from the USP itself, and of course they're very interested in the process, and also from Merck. Okay, so this is what I was going to mention as far as this presentation is concerned. Now I may have maybe a couple minutes. I just want to mention a couple of other projects. Again, I will not present anything, but at least the title. Yes. I mentioned before that the industry, the pharma industry, utilizes a number of legacy systems that are typically baffled in such a way as to be adaptable to glass line vessels. So glass line vessels that look like this, bluish, vessels in which you cannot put baffle against the wall, at least until very, very recently, because of mechanical issues and fabrication issues. Therefore, and on top of that, of course, these tanks are typically provided with a totally spherical bottom. So in previous work, we determined the power number for a variety of systems in which we use the retreat blade impeller, such as the one depicted here. That is the most common impeller used in the pharma industry, because again, it can be coated. And we found out, of course, that there's a difference depending on the baffling. So if we use 4 baffle, which is not typical industry, we get the blue curves. These are all experimental. We got the single baffle in the middle of the vessel, or between the shaft and the wall. We get the red points. And if it's complete baffle, we get the greens. So and we also simulated this, and I will not go into that. But the objective of this work was to determine experimentally the power number for an RBI, retreat blade impeller, for a number of different partial baffling conditions that are commonly used in industry. These are the type of baffling that people find routinely in the industry, okay? Especially in legacy pieces of equipment. So they try to maximize the baffling effect. But believe it or not, we could not find any documentation on the power dissipated by these impellers. So we decided to do it once and for all. So we put this in the lab. We had this fabricated in 3D printed, and we then start running experiments. And I will not go through that, but I will just mention that I think, let's say, for the first time at least that I know of, maybe there are people in industry who have all this data, we don't have them, are some results for the different type of baffles. So these are for beaver tail, D baffles, H baffles, finger baffles. And you can see the simulations and the experiments seem to agree. And here's a summary of the type of baffles and the power number that is associated with that. So I will not elaborate anymore on this. I will only have one more sentence, allow me that, and then I'll stop. That we have also worked at the industrial determination of the NJS using electric resistance tomography with an approach that can be used industrially, that does not need transparent vessels. And we have already published this work, so I will only go to the very end and show you the publications. Yeah, here, if you're interested, they're already out. And I'd like just to acknowledge that this actually was supported by Colgate-Palmolive, which is not a pharma company, but nevertheless are interested in this kind of work. All right, I think I have concluded my presentation, so thank you very much for your attention. And again, I'll be happy to answer questions if you have them, or take part in the discussion section.
Okay, great. Thanks, Piero. Lots of interesting work using academic tools like PIV, and really applied and applying them to pharmaceutical problems. So you'll notice that there's some people that have already written in some questions in the question and answer tab. So when they're quite specific like that, you can answer them directly in there. And we're going to move on to the next speaker now. So we have Thomas Wucherpfennig from Boehringer. Sorry. He's a principal scientist in cell culture process development and at Boehringer Ingelheim. And he's leading the late stage process development team at the moment. And his scientific focus is on scale up of bioprocesses and process analytics technology and modeling. So over to you now, Thomas. Thanks a lot.
Okay, thanks for the kind introduction. I'm presenting you today a talk with the title Mixing and Mass Transfer Performance as Key Parameters for the Scale-up and Transfer of Cell Culture Processes. So as announced already, I'm working for Boehringer Ingelheim, which is a family-owned global corporation dealing in human pharmaceuticals, animal health, and biopharmaceutical products. So the area where I am working at. So what is actually a biopharmaceutical product? So it can be any biotechnology-based medicinal product which is not extracted from any biological source. So it can be proteins, nucleic acids, also live microorganisms or attenuated fragments thereof. The first product was actually the human recombinant insulin, Humulin from Genentech from 1982, basically already. And in the European Union, there's an additional criteria that the product needs to be produced with recombinant techniques. So if you look at the product in itself, you have like a standard small molecule, so to speak, which could be acetylsalicylic acid, which would be dead. And then on the other hand, you have your antibody, basically, which is mainly produced in your cell culture processes. And this is also something I'm working at. And you see, this is quite a large molecule and quite hard to produce, not possible these days without a cell culture process. Maybe in the future also by printing, but let's see about that. So looking a little bit into your biopharmaceutical process in itself, you divide basically between the drug substance and the drug product. So basically the drug substance comprises the genetic engineering, the development of your cell line, your bioprocess, your upstream cell culture process, then your downstream purification process. And then it moves over to drug product, where you have your formulation, basically fill and finish, putting your product into your final buffer, doing your QA, and having a fully labeled product developed then for marketing and shipping. So what about the upstream process? So this comprises basically the creation of a vector comprising also the product to be expressed. Then you have to create your cell line. So you transfect hundreds and thousands of cells, and then you have to find the cell which actually produces the most, has the highest productivity. This process then basically is scaled up. You use these cells for process development. For that, we use fully automated bioreactor systems like the Ember 15 here or the Ember 250, which are basically fully automated bioreactor systems within a bench being operated by a robotic arm. And then we also use this standard top bench, and then later on it goes to stainless steel systems or also disposable systems. So after the transfer for the first production of clinical material, then you go over to manufacturing in your final scale. So when looking at your cell culture process, there are very, very many parameters which actually influence your process. You have the seed density, for example, the cultivation time, pH profile, temperature. It can be the media, the mixing, of course, is important, the feed, the agitation, and the aeration, which are also your classical scaling parameters. And if you look at the different vessels, I mean, all kind of vessels are used in the pharmaceutical industry. So as I covered already, you have the fully automated Ember systems. Also, you can have disposable top bench systems. Standard is 3 liter, and then stainless steel. Larger lab scale, I would say. We use that for consolidation of our processes. And then you can also have disposable larger scale systems up to 2000 liter, which are basically stirred plastic bags in a stainless steel box. And then there's also your standard stainless steel fermenter, which we use up to 12,000 liter usually. And of course, all of these vessels will have different characteristics, and especially for disposable, since we also heard it in the last call, you seldom have any baffles, And it's also apparent that if you look like at the Reynolds number, also in the small system, so they won't be fully turbulent at your standard cell culture processes. So this is something just you have to be aware of. And to cope with that, basically, we characterized all our systems, at least the bioreactor systems, also the old ones, and have a center of excellence there in Biberach, also having characterized systems from other sites in the US. Or in Indiana or Shanghai in that case. And we also do have CFD models for all our bioreactors, because at the end, the scale up is based on parameters from the CFD at the end. Since validation of these models, of course, is of tremendous importance, and this is also true for the very large scale, we have constructed this full-scale transparent bioreactor at our cooperation partner at the Technical University of Hamburg-Harburg, so Professor Schlüter's lab. And we use this large-scale vessel here to validate our models. We've done that for our power number, which gave a very, very nice fit to our simulated power number, and do also lots of mixing time simulations and validations over there. And I've also brought you a movie here in this next slide. So it's actually pretty amazing if you see in full scale how your agitator is working, and how the dispersing of your aeration actually works, because of course in a standard stainless steel you can't really look into the vessel and see how the process performs. And what was most amazing for us here, I apologize that it's going a little bit slowly here, was that you see just so many bubbles here. I cut it in myself, and you see at standard operational conditions just a bubble curtain, so it's even hard to look in there. So talking a little bit about the scale up of bioprocesses now. I mean, when scaling up about from the lab scale to the industrial scale, going over a pilot scale, usually you have several options, of course. Geometric similarity is one. You have your tip speed, superficial gas velocity, KLA. You can do the CO2 concentrations, which are rather critical for cell culture processes. You have your mixing time, and also shear, which your standard mammalian cells are rather sensitive. So let's look at the sparging first. And you will see now between lab scale and industrial scale, the sparging, I mean, even if you put the same volumetric sparging rate, it's not really the same. So here you have very little dispersing power, just a few bubbles in the system. And here you have thousands of bubbles in just this area over here. So even if the KLA will be very similar, which it is at standard process conditions, you see very clearly that the conditions will not be the same in both systems. And this is also what you can see in the processes from time to time. So basically, if you look at this small scale system, you just have a different ratio between your stirrer plates to your bubbles, as you have in the large scale vessels, where you see these large vertices forming here, which also have the impact on the mixing, basically. So you have the same volumetric gas flow rate and specific power input, but very different gas loading capacity. So let's talk a little bit about shear rates, since they also important scaling criterion. I know very often also a scale up of by tip speed is common, at least when not going to the very full commercial scale. And here we have worked together with the UCT in Prague, actually. They have this shear sensitive aggregates, which they use as probes. They are approximately in the same area in size as your chode cells. So your chode cells are a standard from 11 to 17 micrometers, and your PMMA aggregates are 2 to 20. And basically, you create them in a small vessel, dilute them, put them in your vessel to be examined. Then you have a certain kind of agitation speed and aeration for around 2 hours until the readout is constant. And then you analyze how your particles are decline in size. And from that, you can calculate basically via a calibration the shear stress. So we've been using that to analyze most of our bioreactor systems. And we've been using here also surfactant as a protective agent doing the experiments with the breakage is affected by bursting bubbles attached to the aggregate surface. So this is also a topic which has been published in literature and is known. We checked here that the surfactant is actually high enough within our cell culture media to not influence the cells in any negative way, but with the concentration we are using, actually aeration doesn't have an influence anymore on the shear rate. So basically what we found here is that only the tip speed here influences the shear rate. So in the very small, the lab scale, we went very high for cell culture conditions in industrial scale, we were also able to go quite high here. And this red dotted line here is actually our platform process, which we characterized. And what you see, of course, is that with the upscaling, the shear stress also at the standard P by V, which is the scale-up criterion here, is basically increasing. So also, yeah, shear rate, it's also won't really stay constant during the scale-up. So what about mixing? We yeah, have the in molecular scale, we have the molecular motion. Then in yeah, rather small scale here, not talking about vessels, but in mixing terms, we have the mixing by the eddies and also mixing behind rising bubbles here. And in large scale, we have the bulk mixing due to stirring, where and also due to the rising bubbles, which is by Janssen trafficking, so like an airlift or a bubble column. So the mixing time then is the time to reach a certain homogeneity within the reactor after a step change, and it depends on the tank geometry, like the diameter, for example, aspect ratio, the presence of bubbles, and the stirrers, of course. Then also the specific power input and the superficial gas velocity. So at a rather low gassing rate, you have more like a loading regime. So basically your bubbles will follow your bulk motion. It will behave almost like a single phase in that case. And then you also yeah, differentiate between this high gassing rate, where you see a flooding regime. So the bulk motion is buoyancy driven, and you see a decline of gas hold-up and of power input. So this will influence your process. It will see you will see a different mixing behavior. And we found that for our cell culture processes, this transition between the flooding and the loading is really important for the mixing time. So we came up with these correlations, which are, of course, not too easy to read. However, you can have yeah, certain agitation rates, which are depicted here by the Reynolds number, and aeration rates, which you see over there by the symbols, which lead to conditions within your bioreactor where you increase your stirring rate and your mixing time actually increases, but not decreases. So this counterintuitive behavior. And on the other hand, you can have a rather fast stirring, so high agitation rate, but a slower mixing time. So we can divide the processes here in a rather heterogeneous regime. So if you're operating in there, you don't really know what happens if you increase or decrease your aeration rate and your agitation rate. So you can actually increase or decrease your mixing time depending on where you operate. And then you have this more or less homogeneous regime where yeah, the system in itself behaves as you would expect. So meaning high agitation rate leads to this faster mixing. Then we looked at some actual process we were running at that time and found that actually half of them, yeah, rather the older process were actually in this heterogeneous regime, and half of them were in a more homogeneous regime. So it has really some relevance, these studies, also for manufacturing. So it's important to know for your system to know where this yeah, transition takes place, to yeah, calculate where this transition point will take place, because I mean it can be present within the reactor dependent on the steering and the aeration. And the flow number and the fruit number are important to actually calculate this where this transition from the homogeneous to the heterogeneous or vice versa takes place. So it has, the study has also been published 3 years ago. So when looking at the picture here, also of this homogeneous heterogeneous regime, on the one hand here at 30 RPM, you can have a rather fast mixing time at P/V, which is below 10 watts per cubic meter. And 26 seconds, I mean, it's a pretty fast mixing time for a 12,000 liter vessel. And on the other hand, you can put 100 watts per cubic meter into your system, same aeration rate, and you see much longer mixing time. So it's doubled basically. And that's because you have the formation of a lower compartment here, which stabilized at this higher agitation rate there. So you have a homogenization of this two-phase flow, which leads to a stabilization of compartments. And this was a topic we also wanted to study in more detail. So we set up another method. Basically, the mixing time determination here was mostly done optical. So it's based on the blending of an acid and the resulting pH change. And this neutralization reaction is visualized by means of a pH-sensitive tracer, which used to be the phenolphthalein, which has this pink color, and goes then from the pink to the white transparent. And we introduced a new tracer, the bromothymol blue, which has different colors from blue over green to yellow. And with this different tracer, we are able to also look at more details than before. This was also, the study was published early this year. So basically, when homogeneity is achieved, the decoloration in the entire system is achieved in each fluid element. So it's micromixing. So at a acid-base ratio of 1. And if the acid-base ratio is greater than 1, the decolorization is actually no longer coupled to the homogeneity in the system. And it's more a measure of the macro mixing. You see that over here. So it's also been done in the past, as you can see over here. So basically, we found that at acid-base ratio greater than 1.25 onwards, you can clearly see the compartments. And this compartment formation probably is due to large-scale coherent structures, and we want to investigate these, of course, now in the vessels of different sizes. And with the visualization of the macro mixing, the mixing history can be illustrated. So also, we've looked at different steering frequencies and aeration rates. And of course, the mixing time decreases with the higher agitation rate here. But what's interesting is that you see a really high self-similarity between the different stereo frequencies. And the color map looks like a footprint of the reactor setup. So basically, we want to drive this now here further. You only also see this homogeneous and heterogeneous regime in this smaller scale vessel. So same aeration rate here, but same steering rate, but slower mixing time in this heterogeneous regime in that case. And it's also, the system is very rotationally symmetrical. So we want to now use that for different vessels and also explore optimization potentials in terms of the geometry. By the way, we also did simulations there with the lattice-Boltzmann code, and we're able to really well replicate what we saw in the measurements. So if you're interested, you can have a look in the publication. So basically, to wrap it all up, so physicochemical parameters in small and large scale are different, and not all phenomena seen in large scale can actually be replicated in small scale. And the key is to know your equipment, have it characterized, and know what your processes, what your cells will expect in the large scale. And then, of course, you have to select cells which are robust and can cope with large-scale environments. And if you know what to expect in the large scale, you want to stress your cells in small scale and then select the ones which are robust also at the large-scale conditions. And this was also my last slide. I thank you all for your attention. Thank you.
Thank you very much, Thomas. I really enjoyed listening to, we know that mixing is not easy, and I think you just showed the difficulties in scaling up, and particularly the counterintuitive aspects of gas liquid mixing. Very interesting. So now we're going to start the panel discussion. Okay, so as I mentioned at the beginning, but there might have been some people that weren't connected in the beginning and now have. We have three panel members. We have Suzanne Kresta from the University of Saskatchewan, where she's the Dean of the College of Engineering. We have Harry van den Akker, who is Bernal Professor of Fluid Mechanics at the University of Limerick in Ireland. And we have Mounir Bouafi, who is Senior Fluid Mechanics and Process Modeling Engineer at Solvay in France. So the idea here is that instead of just having, one-on-one questions and answer session, that we have more of a discussion about pushing the boundaries in mixing, okay, in the process industries. So I'm going to just start off and try and spark this discussion. And I'm going to just ask a really general question, and there's probably lots of answers to it. But I'd like to know what are the new challenges that industry is facing in mixing today. So any of the panelists that have speaking opportunity, everyone can discuss this. I will stop sharing the screen. Thomas, can you stop sharing your screen?
Thought I had stopped already. Sorry.
That's okay. I'll put mine on.
Okay.
There we go.
Good.
And maybe we can see everybody's faces.
Yeah, if everyone can turn their videos on.
So there we go. Oh, we've got your screen back, Joelle.
Yeah, that's okay, isn't it? Just a decoration.
It takes away some of the space for faces.
Okay, I'll stop it then. There we go.
It is lovely to know where we are. It's always good.
That's all right. So, challenges. What are the challenges? Suzanne, I'm going to...
yeah, you're going to pick on me because I can always jump in a little bit quickly. That's one of my roles in life, apparently. I was really interested by how we continue to push the boundaries with CFD and how people are doing some really interesting new work. And Thomas, I don't think I've been at a table with you before, so it's lovely to meet you and welcome. Really interested, though, if we could just have a couple of specific questions to start with, Joelle, because I was curious about the aggregate probes, because that's something I haven't seen used before, to look at local shear. And somebody posed a question. It's not just the local shear, but it's the local shear and the time experience that part, right? Mm-hmm. So can you comment on that and how you produce and calibrate those aggregates? I thought it was just a really interesting approach.
I can actually provide you with a publication So the group we are working with, Professor Soos, they have created this, and there's a publication from 2018, I guess. It's Willinger et al. I can also post it, which where they really detailed, they describe how to make the aggregates. And actually, the concept in itself is rather old. So I know from the 70s, there was a clay polymer system used for the same topic, basically. We also tried that, but we weren't really reproducible with the results. So we contacted Professor Soos in that case and switched to the PMMA particles.
Okay, thanks. And in terms of future challenges, one of the things that we keep noticing in this community is the combination between very, very practical work. How do we do a basket that complies with what the FDA needs, but actually makes scientific sense? And then really things that are pushing the boundaries of what is known and new kinds of computational methods. And so I wanted to probe Adam's work a little bit, because that gap in the rotor stator is tiny. And you're talking about fluid structures that are super, we're pushing into coherent structures and turbulent flow research. And so when you calculate the lambda constant, which I think is something that we've used for quite a while, how much confidence do you have in that, and how precisely do we have to get that right to get the right structures in the mayonnaise? Like, it goes from super theoretical all the way to a very practical application.
If you're asking specifically about the gap, that was something that we did with a PhD student, Stephen Hall, with Andrew Patek at Manchester and Mike Cook, and we did actually make up for the inline mixer. Okay, we made up rotors with different gaps in them as well, expecting it to have quite a big effect on the droplet size. Now, in that case, we were working with dilute systems, so we were guilty of the thing that I kind of complained about, that too much of the studies are about. But we were surprised that we found very little effect on gap. So we were changing the gap, from 0.5 millimeter up to 2 millimeters, and it was having virtually no effect on the droplet size. And I think part of that might be the comment that came up in the chat, where how long does it actually spend in that region, and how much of the material actually goes through that region as well. In actual fact, it's not very much. And in some studies, what you see is that sometimes it's better to recirculate faster and push it through the mixer more times than it is to increase the residence time in any one pass as well. And I kind of take that as an indication of is that the material experiences the higher shear regions of the mixer. So although we talk about bypass in a batch,
isn't that exactly
I think there's a bypass also when you talk about the inline mixers as well.
Interesting.
Isn't that exactly what we can find out by means of CFD?
Yeah, exactly. Yeah. No, you're right. Yeah.
And we can just track packages or cell agglomerates, and look how they travel and how long they are subjected to all types of conditions and shear and so. I think that's a great advantage of CFD. I'm just at a little bit there's a lot of experimental advances, because the experimental techniques are improving, of course, but I think you can find a lot more and in more detailed way with simulation, provided that you have developed the tools to the right level. Yeah, there was a remark on I think it was you, Adam, that said that most studies on droplet breakup, on emulsification, were on dilute systems, wasn't it? Yeah, well, you can do it by with computational studies. You can do much more dense systems.
Yeah. Yeah, my comment was partly related to comments some of my colleagues, in Yo Jansen in particular, sort of comments that, you know, when you look at the population balance equations, the way population balance is defined, it's based on, you know, dilute systems with big droplets coming closer together and films slowly forming and thinning. But if the drops are so concentrated that they're already misshapen, okay, because of the close packing, you know, when does that kind of application of that begin to break down? And to be honest, I'm surprised sometimes how well the population balance works for these systems.
And so just continuing on the CFD question, I just thought maybe I can ask Mounir, because you're a specialist in this type of area in the chemical industry. We didn't have a talk from you know, fine chemicals or chemicals, so maybe you can give us some input on that, how you do things.
Yeah, just the point of view from my side that I'm working for Solvay for 10 years. CFD became really a standard tool of design, I mean, for sure. And for a lot of things like single phase calculations, heat, mass transfer, multi-phase with Euler approach. This is our common daily work in 90% of the time, more or less. I mean, how to say that we are all the time asked to give answers in a quite short time. I mean, we don't have the time. I don't have the pleasure to make LAS calculations or WOF as an exception for some cases, but most of the cases I have to give an answer in a short time, in a week or a couple of days. So more or less we are using rounds, models, Euler, when it's a question of multi-phase, and we started also to couple with population balance calculations, more or less. This is our really daily work within Solvay so far, yeah.
Yeah, but large data simulations were long lasting in 20 years ago, but nowadays computers have lost faster, and you have even GPUs, so you can.
Harry, I mean, 10 years ago, I was running some calculations, some transient calculations, quite heavy for an industrial system. It took 2 months of calculations. I run similar calculations today within 2 days. 10 years ago, I was running my calculations on 16, 32 processors. Today, I have the pleasure to run on 2,000 processors. We have a cluster. I don't run on 2,000, but more or less all my calculations, I run on 100 to 140 processors for each calculation.
So that's fast. That is fast. Then you don't have to wait for a week.
Can I jump in and put a little bit of a twist into this, because I'm interested in when the liquid gets to a level where we start to have coalescence, and moving back to the question of what are the challenges we're facing now. And so when we get liquid hold up at levels where we have to consider coalescence, I see that as a normal part of industrial operations. Thank you, Mounir.
Yeah, I mean,
can you comment?
In many cases, all the cases I have been working on, I have 30% of gas, I have 40% for emulsification cases. It's more or less between 30 to 50 between continuous and dispersed phase. This is really the most of the cases. It's never 1 or 2%, never.
So how do we move into that?
Yeah, how do we do it?
What do you most need to know? What's the critical question we should go after first? And this is Adam, Mounir, Thomas, anybody who's working in that regime. What do we need to know most?
Yeah, me too. I had the same question.
I can have a go first.
Yeah, good.
I think the biggest gap we've got is probably in measuring material properties.
Things like rheology, certainly for my type of interest as well, when you get to non-Newtonian. You know, we tend to do rheology measurements in a rheometer, you know, where it takes 20, 30 seconds, you know, till it reaches a steady state, and it you know, high shear meters, it's out in less than a second. So, you know, I think if the systems are relatively simple and they recover really, really quickly, then, you know, rheological measurements are okay. But once you start moving away from that and you get time dependency and structures can reform and you begin to get elasticity coming in, I think it becomes more about how do I represent the material properties and less, I think, about even, you know, exactly getting the geometry right.
Cool.
And Piero, what about in the pharmaceutical industry with, I mean, you've got lots of, I mean, it's properties, but you've got solid liquid flows or things like that. So how do you include that into simulations or into the design process?
Let me take a small detour in answering your question.
Good.
And the reason is the following, because I think, although some of the technical issues may be the same across many different industries, each industry has its own peculiarities. And one that dominates the pharma industry is the fact it's heavily regulated, for one thing, which means you have to go through a certain process. And once the process is established, you're not able to change it, or not change it very easy, unless you go through a quite involved revision process that usually is very expensive and not probably worth the effort, and really have to do it. In addition, at least until very recently, the industry was heavily dominated by scientists, especially chemists. And since the regulatory personnel is typically made of scientists, the role of the engineers here, though it may be obviously in the technical area, is also compounded by the fact that you need not just to address the process itself, but also to convince other people, especially scientists, that your approach is correct. And therefore, you need to literally sell some of these approaches to many of your colleagues and to regulators. So this may not seem like a technical issue, but it trickles down to be one of them, because then eventually you can only rely on certain tools and not others, unless, and this will take place over time, of course, you're able to show with a significant level of confidence that your simulation, for example, capture something that is relevant to the scientists and to the regulators. So in some cases, like the one I mentioned before, especially interacting with people who are industry, but they are scientists, they already kind of have an idea that some of these parameters may be important, but they don't really quite understand exactly why and how. And the best way to convince them is not through simulations, it's through experiments, by showing whatever you have to show that way. Once you have that, if you're able then to use simulation to reinforce the concept, they may start getting used to that and understand that this can also become quite a valuable tool. In fact, I can attest that the role of engineers has increased dramatically in the pharma industry over the last probably 20 years. And especially in the last few years, I've seen an acceleration in the use of some of these tools that now seem to be, be used more intensively, more broadly, and also becoming more acceptable by not just engineers who work in the area, but also trickling down to, as I said, scientists, regulators. But remember, this is something that will require a lot of work. the little device that I mentioned to you, the USP, well, there are several types, but 7 types, 7 types to be precise. But all these systems, well, at least the most important of them people use, are small, unbaffled vessels. Now, we all know that if you use an unbaffled system, any kind of small asymmetry will make a big difference in terms of flow. In fact, I didn't show this clearly, but in my presentation, we spend months trying to eliminate all possible asymmetry in our system to get the best velocity profile we could get. And we could never, ever get 100% perfect symmetry. Now, you can imagine a system like this, in order to improve mixing, which is not necessarily the issue here, because you need to show that there's a certain profile that you can measure. If things happen too fast, they're useless. But a few years ago, I proposed a modest change to one of these devices to put the shaft sideways by 8 millimeters. And we showed this experimentally in computation to a certain extent, that by doing so, the system became much more reproducible, because it would eliminate a lot of the issues associated with perfect symmetry. I don't think people care, quite frankly. I mean, it seems like simple solution. You don't even have to change equipment. We devised a small modification to the gizmo that would push the vessel sideways by this much. The flow will become much more asymmetric by just doing that, and the system will become much more reproducible.
Don't tell the regulator.
But you think, exactly, you think that the US people say, sure, oh, that was a great idea, let's do this now. Because they won't. And so
Piero, I think this points to a bigger issue that happens every time we try to cross disciplines or collaborate with people in other fields or work with industry or write a handbook. People speak different languages and have different working cultures, and it can lead to some really, really challenging things that turn out to be communication barriers and vocabulary, and that are partly driven by different cultural expectations. So there was a really great article that told the story of moving from the understanding of droplet spread to aerosol spread around COVID. And they actually had to call in a scientific historian to go back and do some forensics to figure out where the misconception came from. So I think that as soon as all of us heard that it was an N95 mask made by 3M that was needed in the most high-risk applications, we all knew it was aerosols. I certainly did. The people I work with in biosecurity certainly did. And so we knew it was aerosols in about April, but on a subconscious level. And it turns out the people talking to the regulators had this huge problem of a failure of vocabulary, a sacred cow that had been built up by somebody with a big name, and they had to go back and find the original references to untangle the problem and convince them to move forward. And so I think that that cultural connection and the ability to try to move across that is just holding us back in a lot of places. And I would put that right up there with high hold-up systems as something we just need to be aware of, because I run into it. I've been working on that for, when did the handbook come out? A scary long from Claudio, and I'm just wondering if he can jump in and tell us some of the things he's thinking about for the future.
I have some questions, if that's okay. I'm mostly thinking about education lately, as you may imagine. It has been 5 years since I started here, but still a big issue. That I worry that things are becoming a little bit more complex, and we have challenges that become bigger and bigger. how do we ensure that the newly graduated engineers have the skills that are required nowadays? And I think this is a question for both the industrialists and the people who are working in academia as well. What would you like to see from new graduates and people in academia? What are we doing to ensure that they have the right skills?
I think I need to jump in at this point, if you allow me. Because I was about to mention in response to Suzanne's comments that one way to address some of these issues is through education. And I don't mean, PhDs. I'm talking about simple statement of facts that need to be transferred across the barriers that Suzanne was mentioning. Just a simple example. I was invited, I gave mixing courses in industry, and at one point in time, we're talking about some time ago, I was invited by an engineer who had worked in a different company where I gave one of these seminars, actually workshops, to a smaller sized company in the Midwest. And so he invited me to give a course of mixing. And most of these people were chemists. So I had this deck of slides, starting with the very basic, this is a motor, this is a tank, this is the impeller, and baffles. But what are baffles? This is a mid-sized pharmaceutical company. Okay, people do not know what baffles are. I show a video, the famous video in which you have baffles going in and out, and you could hear the audience say, "Whoa!" Well, about 100 kids. So these people had no concept of that. And again, now I think it's trickling down a little more than it used to be, but there's a significant portion of this kind of education you need to make to apply to a whole group of people that otherwise ignoring simple facts of life, so to speak. So education in a general sense applies not just in terms of formal education, newly graduate, but also in terms of cross-discipline education. Okay? Yeah. And I'm not sure how easy that will be, because especially as we move along, we live more and more in silos. And that makes this transfer even more difficult, because everybody's so specialized and can do, this, that, but doesn't communicate very well. So I'm not sure how to do this, but this kind of dissemination of information to people who are kind of not in the mix, it is critical. And then plus, again, one thing, and I'll let you talk, Suzanne. We don't teach mixing to engineers, so that's the main still problem. So,
but that's a different problem.
That's a different problem. People, yeah, absolutely. And in the US, at least, the people working on mixing are decreasing at a very fast rate. Okay, and probably most of them are my age, if at all.
But there was a time that chemical engineering was big on universities. It is no longer. And only when chemical engineering was big, you could afford a separate course on mixing. Now, chemical engineering has grown smaller. There's no room for a separate module on mixing, and it should be part of pharmaceutical engineering or biochemical engineering. So you should find different vehicles to pass the message about mixing.
So I'm gonna jump in, Harry and Piero, and throw a little bit of a rescue line to Claudio, because we've been saying these same things for at least 20 years. I think what we're moving towards at the how do we get out of a budget constraint? How do we get out of some of these other constraints? And I think what we have to do is actually change the way we think about universities and look at our undergraduate programs and shrink them down to the core concepts and skills. And that's the part that we put through accreditation processes. That's the part that everybody has to take, and that's the part where we concentrate government funding. But then we have all these specialties that people need to be able to drop in for shorter intensive courses, for courses that have undergraduate students, graduate students, and people from industry, which is the most fun I've ever had teaching. Because when you get that kind of mix in the room, the ideas just flow really well. and you start to get these conversations that break down boundaries. And we need to get out of it the idea that we're going to train people to be biochemists and engineers. That's just too much education before you can do anything useful. We have to help people talk to each other better. And so this is something that, you know, we're just starting to understand, but it is starting to penetrate at the levels of academic leadership. And so that'll be a really exciting shift, Claudio, and I hope that it will bring workloads back to a better place for young people so that academic careers become fun and dynamic and light again, because I think that they've gotten harder and harder over the last, since I started. Expectations have gone up, and we have to get that workload under control as well. So I just want to throw you a little bit of a lifeline and say, I think there's hope. I think we can do this better. And I think that we can serve our friends in industry better as well. Imagine being an industrial chemist and being able to come in and do, you know, Piero's short course from anywhere in the world, right? When you need it as a manageable investment. Like, wouldn't that be awesome if we could get together and build the most amazing short course ever, and you can register in it at whatever university you want to tag into. And it's different than a MOOC. I think we've learned a lot in the last year about how we can uncouple time from need to learn. And so I hope we capitalize on that and we take it forward. I'm curious from people in industry, Harry, if I just could, I'd like to hear from them what they see in terms of education and continuing education going forward and how to get mixing into their cultures and what's worked for them. I know that academics can go on forever. We get paid for that. But I know that a lot of people in the room want to hear from the other side of the table too.
I mean, Suzanne, just from our side, I mean, me and my colleagues, we used to go to universities and talk to students. That means, at least I did it with my colleagues at Toulouse. I did it here in Lyon, and even in Rouen also. So yeah, it's a good point. Yeah, the positive thing that we bring good students as master students, and if it goes good, we hire them as PhD students, and this is a good, yeah, it's. But what you mentioned, it will be nice that we make this more interactions between academia and industry, and it's yeah, because students.
From an industrial point of view, is CFD becoming essential as a module in chemical engineering? Or other types of modeling tools like molecular modeling or mesoscopic modeling?
That's an interesting question. So I come at modeling, you know, as an experimentalist. That's what I've done for most of my career, and I actually view things like CFD as another experiment. Okay, it's just an easier experiment to do, because I think one of the things that's become painfully obvious to me is, you know, you tend to come in and you say, well, the experiment's right, and if the CFD doesn't agree with it, the CFD is wrong. And you never question the experiment, yeah. And you know, as we've gone through, you know, sort of generating data after data, the way that we analyze it, the way we make corrections, you know, just the method itself sometimes introduces far more errors into, yeah, well, errors is the wrong thing. You end up with very, very different numbers depending on how you analysed it, and you know which data you've chosen to include, which data you've chosen not to include. So I think CFD, I think it is changing, because it is now, you know, relatively easy to do it, but you still need somebody good to do it, in the same way that you need somebody good to do a proper experiment as well. And that both of those things require training. I think
maybe sorry.
No, it's all
I
right.
just wanted to comment on exactly that, because I mean, we're using power numbers at BI. We're using power numbers from CFD just for that very reason, that depending on the scale, we saw so many deviations with the measurements of the power number. So we decided to use the CFD using exactly the same method for all tanks, and use that then for scale up. And concerning your earlier question, I guess it's getting more and more traction. So CFD is, and also the other modeling tractions, topics. So when we started at BI, like 8 years ago, I mean, most companies were not doing it, at least from the biopharmaceutical companies. But nowadays, I mean, almost everybody I know is doing it. Not all internally, some do it by external partners, but most have studies on that, yeah. And I've even heard about in auditions, FDA asking about mixing of certain vessels, which hasn't been the case for quite a while.
Many of you will know that that I've moved to Ireland, and that I'm part of the SSPC. That's a research center, Irish Research Center for the pharmaceutical industry. There are most chemical pharmaceutical companies are in Ireland, and they are taking part in that research center. Traditionally, of course, there's an experimental bias. But there is more and more interest in modeling and simulations, and also in making digital twins, so that you with simulations you really give a dynamic view of flow fields, that people see what's going on in the vessel, whether it's a small one or a large one. But then you need dynamic simulation. No steady state with a nice flow lines, but really moving flow fields that people can understand, that the differences in bubbling, having a free vortex if there's no baffle, or if there are no baffles on the wall, or just a single thing, what is it, beaver tail baffle, what the effect of the aeration ring is, and all that type of thing. So then, but then you should really do dynamic simulations. I did that also for the dairy industry with pneumatic transport of solids in a line. And if you do that dynamically with EEM and so, then you can visualize how the transport really goes, and that helps a lot for the dairy industry to understand how that works, and that it is similar to what they see in some very transparent section of their line in the dairy plant, and you can easily show what the effect of increasing flow rates is, and so working with digital twins with dynamic flow fields, I think that is an important educational tool, also for people who are not familiar. We're not chemical engineers or mechanical engineers, but I have a chemist or a pharmaceutical pharma background. I'm happy that I'm there, and there's a lot of
Great. Okay, well, I'm just looking at the time, and we have gone over time. We did start late, but I've really enjoyed this discussion, and I think we're going to have to wrap up now, because people have, put in their agendas that it was finishing at 6 p.m. and it's now 6:10 p.m. So I'd like to thank all of our speakers and our panelists. I'd like to thank also Claudio, who was with me in organizing this. And I'd like to thank everybody that has joined us to listen. I know that some of the questions weren't answered yet, and we'll see what can be done about that, but I'm not quite sure if we'll be able to. Maybe some of the speakers can just have a quick look and see if they can answer quickly. But otherwise, we'll conclude now. So I'd like to thank everybody.
Maybe you can send these questions to the panel members, and that.
Yeah, I think we can do that, because they're all they're written in the screen, so I can send them out. Okay.
Yeah, I tried to answer the questions the best I could when I came in. I tried to answer the question, but I thought I was going to discuss them now, but now there's no time. So any other way?
Yeah, I know, and it's difficult to manage everything, and there's lots and lots of questions when you have 90 people connected at one stage. you know.
Well, okay, so let me
I
at
think
least
we did a
mention that
good
if
job in
people
education.
want to ask more the question, they should email us. Maybe that will.
Exactly.
Yeah.
Yeah.
Okay. Thank you.
Okay. So thank you very much, everybody.
Yep.
And tomorrow morning, for those in Europe or in Asia who can connect, and it won't be the middle of the night for the North Americans or the, you know, all the Americas. We have the awards ceremony at 9 a.m. at Paris time, and we will start on time because we won't have the technical problem. Okay.
Yes,
See
Thank you,
you.
Joel. Thank you, Claudia.
Bye-bye.
okay, bye-bye.
Thank you.
Bye.